We have quite a few people coming into this one live, which is really great. So that is just so fun to see everybody. And we will let people in out of the waiting room as they come. So my name is Erin Breen, and I work at the Math Institute with our good friend, Mike Waske. Taylor Skorick is also here. She's our new colleague because thanks to all you guys, we are getting really busy. And so we had to bring on some extra help to get everything done. So that's good news for us. So tonight we're going to be talking about the importance of materials in a Montessori environment. And I love this topic so much because it really spoke to me when it was first introduced, when I first started working at Great Work. The fact that you can present math in a different way, that you can present math to a mind that didn't naturally get the abstract right away. It was such a beautiful awakening for me to realize you can see it with the materials concretely. And so I love when Mike talks about this because I just think it's such a beautiful way to present and express math. We are going to record this this session, and so it'll be emailed to you guys, or actually we might just make it available for you on YouTube, but you'll somehow or other you will get this recording. I also want to say we have such a wonderful international, global presence with these sessions. So if you wouldn't mind taking a moment and putting in the chat where you are calling in from tonight, that just really fills our souls. So thank you very much. And then the very final thing I'll say before I turn over to Mike is our last session next Monday of Math Mondays will be either seminar or an overview of geometry. So if you could also at some point just put that in the chat as well, so that we can do a quick tally and see out of the 60 folks that are on the call, whether you would prefer Mike to talk about seminar or an overview of geometry next time. So that's it for me, and I'm going to turn it over to Mike, and let's enjoy some importance of materials.
Thanks, Erin. Hi, everyone. Nice to see you. I love some of your pictures. These are great. I think at first everybody was very serious, and now we're getting some really really creative and fun little screens there. So I appreciate that. As Erin mentioned, I'm going to be talking about materials in the Montessori environment and really taking this from elementary to adolescence. And so I have a little presentation that I'm going to share with you. So let me go ahead and do that right now. Okay. And I can't see everybody. Hold on a second here. I got to figure out how to do this here. I like to see a couple faces. Okay. So I'm just going to start by telling a little story. Several years ago, I was visiting my parents, and they were helping us. We had to help clean out their attic. They were doing some remodeling, and up in the attic were all of our childhood toys and all of our things like that. And so as we're going through these boxes, I came across one box, and there was, I was to see what was in there, and there was this wooden puzzle, and it was, you know, big pieces, kind of like an inset puzzle, and it was like a rabbit wearing a diaper, and like it's the strangest thing, but like I haven't thought about that puzzle for like 30 years. And when I saw it, it was just like, oh my gosh, like I was transformed back to being like 5 years old. And I remember like the color of the pieces and the way it was. And then I'm like, wait a minute, I know there's more puzzles like this. And then, you know, I couldn't remember exactly what it was, but I had this feeling of what the next puzzle was. And it was, there was one with a little veterinary scene where there was a nurse and a veterinarian and a dog on a table. And I remember that the table was, it was a piece that was like almost rectangular. And then the dog like sat on the table. So the bottom of the dog was flat. And then the tail kind of hung over the edge. And I remember how that piece felt, like running my hand and it being like a right angle, but like on the inside, it was such a strange feeling to that piece. And more so than that, just by touching those, like, the backs of the pieces were kind of like a little bit rough wood, and the way it smelled. And I probably put those pieces in my mouth when I was like 3 and 4 years old, like a million times. But it just struck me how something that I haven't seen for, for 30 years or so, and how it was out of my conscious being, like just came back to me. And it was just like feelings of sense and touch and some emotions and everything. And again, if I showed those puzzles to you, and even if I saw a puzzle today, it wouldn't have any meaning to me at this point. I wouldn't have any meaning to any of you. But maybe you've had experiences like that before, where you've seen something from your childhood or something, or maybe there's a smell or something that you haven't smelled like in a really long time. Maybe it's like your mother's cooking or a fair when you were little. There's something that takes you back. And it's just amazing how those experiences really stay with you. And and there's something powerful. It's natural, that's something that human beings, we're formed at such an early age, like who we are and what we take in. And even if we forget what those things are, they really stick with us. And I think that's one of the things that Montessori really hit upon with the idea of using material so much in the classroom. And we can take advantage of the power of the tactile, of that emotion, of the way that human beings really learn. We learn through experiences, not through watching or listening to somebody else's experiences. And so often school is us listening to the teacher telling us what to do or what they did or what somebody else has done instead of doing it ourselves. And so, I want this click over here. All right. Okay. So
Hey,
students
Mike.
have strong connections through work of the hand. And on the right here, I have a picture from an elementary classroom where they're working with fractions. And one thing that they work on is equivalencies to see if which fractions are equivalent to each other by taking the pieces out and putting a shape back in. And if it fits in perfectly, then those are equivalents. And so without doing any numerical exploration, it's just a physical, tactile exploration. And then they'll do the recording with the numbers of the pieces, and eventually they'll make the connection between doing it abstractly and concretely. But
Hey, Mike.
Because
Mike, can I interrupt you for a second?
Yes.
I'm sorry. Can you move the panel so that we can see because we can see.
Oh, you can see my panel?
Yeah, we can see your panel.
I didn't know you could see my panel. Okay, that's great. Then what I'm going to do is I'm going to close my panel, and then because I can't see my mouse, and so I can't drag it around, so I can't grab it to move it when it needs to be. So Erin, if anything comes up, just let me know.
Looks good now. Thank you very much.
Sure, because I can't see anybody or anything. So, so when we have these pieces up there, even as an adult, if I didn't tell you that was 3/5, it looks like the 1/3 piece would fit in there. And when students go ahead and they try it, like that's what you would do is they say, well, find the piece that would be the same size. And you want to try a third, but it doesn't fit. It'll be a little bit loose. And so you'll see students try it again and again, the same piece over and over again, kind of hoping like it fits this time. I've had that experience before with like a puzzle. You try to do a jigsaw puzzle and you really want those two pieces to fit together. So you kind of like jam them in, or they're a little bit loose and you're like, come on, this, I really want this to fit, but it doesn't. But the idea that 1/3 is not equivalent to 2/5, they can get these physical experiences here, and knowing fractions through them as pieces, knowing that they have a certain size. So like the 1/4 should feel like a right angle. Like you just know that it's a circle and it has that right angle for that quarter piece, and what the half looks like. So often there are so many students that go through that learn math and see 1/4 is just a 1 and a 4. It's not really connected to anything physical or real. And then when they want to do things like add or multiply or just understand the quantities, they really don't have anything to grasp it on. They might know their rules, but don't really understand what it is that they're doing. Here's a material where students calculate the area of a circle by splitting up the circle into a lot of pieces and trying to make a rectangle out of it, or something close to a rectangle. And when you have these visuals of how to do things, rather than just the letters in a formula, but you have a picture, that really helps with memory and retention. Because if you ever forget what's the area of a circle, but you've done this activity over and over again, and you've written about it, and you've seen it, and you've explained it, Then when you forget, you can say, wait a minute, I can take the circle and I can arrange it this way. And so what are the parts of it? And you can recreate the formula. But you can only do that with the visual. And I'll share an example of this at the adolescent level in a little bit. But without the material piece to it, and if you forget area is pi r squared, like you have nothing to fall back on to remember it. How do you know it's not pi r cubed, or is it pi diameter squared, or 2 pi r? Like, what is it? And you're just memorizing letters. But here with the visual, it's so much easier to have a picture and then interpret the picture. That's a really powerful thing for our students. We also represent numbers as physical amounts, and not just in counting, but we do it with squares and cubing numbers that you see here. This is from the powers of 4, from the bead cabinet, the powers of 4. And when you can see numbers, when you can see the amount in front of you, that helps with mental flexibility. To be able to see a number like 64 as both a cube and a square. Because you've seen 8 times 8. You've seen the square a whole bunch of times, but you've also seen the cube. And so you can take these objects and manipulate them mentally. And that is just so important, that these just aren't a 6 next to a 4, but you see these things in different amounts. So for example, seeing 12 as 10 plus 2. So here's an activity where students might add 2 numbers together. They exchange for 10s when possible, and they have something left over. So seeing 12 as 10 plus 2, or do you see 12 as all these different arrays? And so here we see it as 1 times 12, 2 times 6, 3 times 4, 4 times 3, and 6 times 2. And oftentimes in elementary, students will learn their multiplication facts, and the teacher might not do this activity for the students, because they'll say, well, they know 3 times 4 is 12, and they know 6 times 2 is 12. So why would they bother making these arrays? And it's important because we want to be able to see, not just know what 3 times 4 is, but it's how do we see 12? Do we see 12 as 10 plus 2? That's great if you're doing addition. But if you're dealing with multiplication or division, then you want to see it in these ways right here. And having this powerful understanding of what these numbers are helps out so much later on when students do work in algebra. So here's, for example, students are going to factor x squared plus 7x plus 12. And the key to this work for the adolescent, to learn how to factor this, which is to write it as a product. It's a very important thing for students to solve equations and to do graphing and all kinds of things, but we do it geometrically with materials. The key to factoring this is knowing that that 12 can be arranged as 4 by 3. Because what's 4 plus 3? 4 plus 3 gives us 7, but 4 times 3 is 12. And so to have that flexibility to see 12 as, well, it's either 6 and 2, or it's 4 and 3, or 12 and 1. And just to know that about 12. Like 12 has a character about it. Whereas, a number like 13, like that's a prime number. And so that should feel different than 12, which is highly divisible. Or a number like 10, which only has 1 pair of factors. Because if you deal with those factors over and over again in a physical way, you really understand the character and the quality of those numbers. And then students have that flexibility to use it in new ways. So when we get to doing algebra with students, when we get to doing more advanced geometry or advanced work with number, students already have this ingrained in them. And it's not a struggle when I say, well, it multiplies to 12. And students are like, well, maybe I can divide it by 5, or can I divide it by 7? Like they don't really know that instinctively. So the more students do that early on, the more it pays off later. Then we can focus in the adolescent level on the higher concepts, because those other ones are really ingrained. And so when the materials become internalized, when students really understand, when it's kind of a part of who they are, like that, like those puzzles were for me, then that leads them to abstraction. And that word abstraction really means to draw from. You're taking the essence of what things are, of number, and you're drawing out from there. And if you don't have something physical, you can't really draw anything out. And so a lot of times people think, well, you're going to work mentally, you're going to work in abstraction. And what that basically means then is working, what does that mean though, right? It's not just like Well, let me show an example that'll best illustrate what I'm trying to say here. But before I do that, this right here, this is an activity students will do to make tens when they do adding. And so we see that 5 and 5 is 10 on the left, and then they have a 6 and a 4 to make 10, 7, 3, 8 and 2, and 9 and 1. And when the students do this over and over again, they're making tens, and it's like they're filling something up. And, if you have something that's almost filled up, like you have 9, that just really, really wants to be 10, or 8. You're just like, gosh, I'm just too short of being a 10. And so when students want to do something like add 18 plus 45, and we say, do this mentally. What a lot of people think this means is to imagine like we would in the algorithm where we add numbers together, add 2-digit numbers on paper, where we take the 18. Aaron, can anybody see me, by the way? Because I'm making hand motions and I don't know if anybody can see. Can everybody else?
I can see you across the top of my bar. I think it's just
okay. You have a
how
bar. Okay, that's what I wanted to know. Okay, I don't understand how Zoom works still. It's only been a year, everybody. Sorry, I just want to make sure that if I'm doing things to illustrate with my hands, I just wanted to know if I was being seen.
No, we can see you.
Okay, great. So when you have 18 plus 45 and say add this mentally, a lot of people think it's like, okay, put the 18 on the top, then the number 45, then add the ones column. So, if you're trying to do this without looking at the numbers, you imagine the 18 and the 45, you have to hold it in place. The 8 and the 5 is 13. You put the 3 down, you put the 1 up, then you're like, well, wait a minute, what were the other numbers? Then you're adding and you hope you get it right. And people think that those who can hold those numbers like that in their heads are doing mental math. But all that is, it's doing paper and pencil math in your head, and that's different than actually adding. So for a student who has experience with materials, they can imagine 18 and 45 like this, where they imagine the bar of 10 and the bar of 8, and then they imagine 45, so 4 10s with the 5. And that 8 in the 18 is just screaming to be filled in. And so if they had this mental flexibility because they've done it physically and now they can do it, they can imagine what would happen. They say, well, I have 5 left over there. If I just take 1 and put it over here, and I can take another 1 and put it over here, now I have 2 full ones. And I can remember there's 20. That's 2 full bars of 10. And then over here, I have 4 full bars, but I only have 3 left over. And so that gets us 63. And I will take, and that kind of mental math where you're taking 45 and you're, nobody teaches you to like take 2 from that and add it over to the 18. That's not a technique that we would teach in students, an algorithm to add numbers together. But when you have physical materials, this is the most natural thing to do. And so now to add 20 plus 43, that's very simple to do. You're just saying, basically you're adding 2 plus 4, right? It's 2 10s and 4 10s is 6 10s. So it's going to be 63. I'm much more confident in adding this way than I am with the algorithm if I'm doing it mentally. And it can be faster than trying to find paper, find pencil, write it all down. These are the kind of things that we want our students to be able to do. Also in the elementary, when they want to add fractions like 2 6 plus 3 6, the way I learned this was a rule. And it's when the denominators are the same, you add the numerators and keep the denominator. Like that's the rule that we learn. And that works every single time. But the problem is that then when you have a subtraction and then you have multiplication, then you have division, then you have mixed numbers, it just all goes out the window. You can't remember what to do. And then what happens when you have different denominators? All the rules get all mixed up. But instead in elementary, what'll happen is students will, when they see 2 6 plus 3 6, they'll go to the shelf and they'll take 2 sixths. So there's 2 of the 6th pieces. They'll take 3 of the 6th pieces and they'll combine them together. They'll literally, what adding is, you put everything together and they'll count and they'll say they have 5 sixths. And then they'll record that. And so students will do that for a while with different fractions. And then all of a sudden, they don't need the material anymore. And they'll come up to you and they'll be like, Mr. Mike, did you know that you don't have to, look, I can do this. And they can just add without the materials anymore because they see what's happening. And what they realize is that, well, the bottom number is just the name of the pieces. And the tops just tell you how many you have. So 2 plus 3 is 5. And you have sixths. So the answer is going to be 5 sixths. And then you can say, okay, well, let me ask you this then. What happens when you have 3 17ths plus 5 17ths? And without making up a rule, just thinking about what's happening here. They can imagine that 17ths, those will be really, really small pieces. And you have 3 of them, and then somebody else has 5 of them. And what happens when you put all those same pieces together? Well, you're going to have 8 of them. So you're going to have 8 17ths. And so there's no need to memorize the rule of when you add and the denominators are the same, add the numerators and keep the denominator. You don't need that rule because you actually have a full understanding of what's happening. Now, from that, you could write about a rule and talk about, how you're doing it mentally. Like, that's great to do, but you don't have to rely on the memorization of those words in order to add, because you have this understanding. And that comes through the practice and work that materials allow. And it's very different than just giving you, 3 pages of worksheets with a bunch of problems on them and say, just do this a whole bunch of times until you can't forget it anymore. That really doesn't work very well for most students. And here, and when students do that, where they just have pages of work to do, what ends up happening is that you give them the rule first, then they practice the rule. This is the opposite. Here, the students are doing the work first, and at the end comes the rule. And once they know the rule, once they discover it through that, and they're like, they can add anything. They don't really need to practice it anymore because now it's boring. It's obvious what to do, and then we can move on. And so Montessori always says that rules are a point of arrival, not of departure, meaning that once the rule is the goal, not the starting point. And the materials allow us to have an environment where that can truly happen. So we've been talking a lot about elementary, and from childhood to adolescence, Montessori says this. She says, because of this vital importance of mathematics, the school must use special methods for teaching it and make clear and comprehensible its elements with the help of plenty of apparatus that demonstrate the materialized abstractions of mathematics. And so I think this is really her saying that even for the adolescent, we need to have materials, because if you're going to abstract something, they have to come from something real, something in the physical world. And our adolescents are great at working in abstraction, but if it doesn't come from something that's concrete, then it just becomes rules. It becomes symbol pushing, and true understanding really it's much harder to get a true understanding for the vast majority of our students without this. And so adolescents, though, will use materials differently than elementary children will. I think this is one of the things that a lot of our adolescent practitioners are former elementary practitioners. And sometimes people they say, well, I know how students use materials in elementary, or maybe they've observed in elementary, and they expect the adolescent to do the same thing, and they don't. And so oftentimes I'll hear adolescent practitioners say to me, well, I tried using the materials with the kids, but they don't want to use them. And that's true. They won't if the materials are taught in the same way, and if we use the same materials from elementary. And so we have to recognize that adolescents will use materials, but they'll use them differently. So the materials have to be appropriate for the adolescent, and we have to have an environment that's properly prepared. And what I mean by the environment being properly prepared, I actually mean 2 things here. One is that we should have materials out and open on the shelves. If we had the materials just in the elementary classroom and we just go grab them when we need them, then that sends a signal to the adolescent that when you need materials, you're really doing elementary work. And so these are for remediation, or because you really can't handle the abstraction, go back to elementary and grab those materials. And that sends a negative signal to them, and that they won't want to use those, quote, elementary materials. The other thing I mean about preparing the environment is that we have to have an environment that's safe, where students feel comfortable making mistakes, where they feel comfortable exploring, and where they feel comfortable using materials. And so as I go through this presentation, I'll show materials that we use for the students who are just starting out, who maybe struggle with math and do use them more like an elementary child would to gain concepts. But then we have materials that our most advanced students used as well. And so when students come into the classroom, and if we have multi-age classrooms and we have a diverse a diverse range of learners in the classroom. And there's one student that everybody knows is, quote, the best at math. And they're using a material because it's an advanced material and it's something that's really challenging for them. Then that sends a signal to all the students that says, well, if that student's using materials, I guess that's okay for me to use a material as well. And so it can't just be done for remediation or for the students who struggle to use materials. We have to find ways to encourage all students to use materials. And that's what I'm talking about, preparing that environment. It's preparing that culture of mathematics, which is equitable for everyone. One way that adolescents use the materials is they'll go from the concrete to the abstract, but then they'll go back to the concrete and then back to the abstract. They'll go back and forth, I think, a lot more than the typical elementary child will. The elementary child tends to work with the materials a lot, and then once they come up with the rule, they abandon them, and then they love working in abstraction. For the adolescent, because they can abstract so quickly, well, sometimes I'll give the lesson, and they look at it, they're like, yeah, I got it. They don't need to work with it. They figured out the rule from my one time showing it. And I'll say it's because of the power of the adolescent, not because I'm such a wonderful teacher that I'm just so good that I just have to show it to them once. That's not what it is at all. They're good at abstracting. But then what happens is they'll continue to work in abstraction, and then they'll either make errors or they'll come to a variation that they don't really know how to do. So then what are they going to do? Hey, let's go back to the materials. Let's see what's happening here. Let's do it physically again. Oh, I understand now. Then they'll go back to abstraction. And so we want to have those materials out and available and know that students won't always be working on them all the time, but they'll go back and forth a lot more. They'll often use them to understand an old concept in a new way. They already know how to do something, but they're going to explore a different aspect of that concept. So for example, they might already know fractions, but they might not understand exactly what's that rule for division of fractions again? I know how to divide fractions, but how does it really work? And so they'll go back and they'll explore that and they'll understand it in a different way. They'll also use it to deepen their understanding. And sometimes that's kind of an indirect way that they'll use the materials, but they have an understanding, but then they're going to go a lot deeper through seeing it physically. And other students will use it as an aid when they're first starting out, especially the younger students, or when there's a new concept that's introduced, they need it to help them discover that rule. And so we have this wide variety of ways that students will use materials. And I think that's important to know, because just because a student understands something doesn't mean that the materials can't give them a lot of benefit. And I'll show some examples of that as we go on. Okay, so here's another, I like thinking about it this way, the difference between the adolescent and the elementary child. Two great mystery people in the world of mystery novels, or in mysteries in general, are Agatha Christie and Columbo. Now, Agatha Christie wrote things like Murder on the Orient Express, and Columbo, played by Peter Falk right here, is a TV show in the 1970s and on into the 80s, where he would solve mysteries as well. But TV show versus books. But if you ever have read an Agatha Christie novel, or my wife, she reads P.D. James and all kinds of novels like that, what happens is that you read the story, and at the end of the story, it tells you who did it. So the whole goal of you reading the book is to figure out who the murderer is, or who committed the crime. And that's how the elementary child works. They'll work with the materials, and at the end, they're like, oh, now I see the rule. So the rule is something they discover when they're all done, and then it's like they close the book and they're satisfied. Now, if you've ever seen an episode of Columbo, and if you haven't, I highly suggest you pick one, because they're fantastic. Every episode of Columbo starts off by you seeing exactly how the crime was committed. You see who does it and how it was done. First thing right off the bat. So why would you stick around for another hour plus to watch a TV show? Because you're watching the detective figure out who did it and how they did it. And here, knowing the answer, like if you read an Agatha Christie novel and somebody told you who did it, like that would ruin the whole book. But for this television show, it adds to the excitement, because you already know the answer, and now you have a different motive for watching the show. It's, can you see how he figures it out? And so knowing it gives you some additional knowledge. And our adolescents work a lot more like Columbo. And they do this for several reasons. One thing is they can abstract very quickly and figure out the rule right away. Again, sometimes that happens as I'm presenting. I'm presenting and they're like, oh, I see that now. That's great. But there still is something in the materials for them to go deeper, to figure out the nuances of it. But we don't want to give up on the materials just because they know the rule. There's still something there for them to work on. Another thing that happens is they'll collectively discover the rule. What I mean by this is oftentimes adolescents will work in groups, right? And maybe in their group of 4 students, and they're trying to figure something out, and one student gets it. They're like, I figured this out. They have this aha moment. They kind of Agatha Christie'd it, but then they share it with their group mates, right? They'll share it, and the other kids are kind of like, oh, okay, yeah, I see how you did that, and they kind of get it, but it wasn't their discovery. So they see their friend do it. Now they know the rule, but they still have work to do to really internalize it because they didn't come up with the true discovery. So now they need to work with materials so that they get that internalization. The internet, man, I'm telling you. Sometimes they just look it up and they spoil the fun. This is another thing that happens with culture, and something that I had to learn is that I give an activity to students, especially students who are new to my class, and instead of going through the activity, they're like, "Oh, I'm done already." I'm like, "Oh, well, how'd you do that?" He goes, "Oh, I just looked it up online. I watched the video, and now I know how to do it." And so we talk about the fact that well, I don't care if you know how to do it. The activity was the point of how you get from here to there. Like that's the part that I want you to work on is how do you think? How do you solve something? How do you see? How do you follow something through logically to get from point A to point B? And so, again, we have to create that culture where that's what I'm emphasizing. I'm emphasizing the process. I'm emphasizing explaining how the material is used, not just what's the answer. So for area of a circle, it's great that you know it's pi r squared, but I'm still going to require you to show me with the material how to calculate that area. Why? Because I want to make sure that you understand the concept of breaking things up into rectangles, because in 2 years, when you get to integral calculus, you need to have that really ingrained. And so there's a higher purpose to working with the materials than just the thing right in front of you. Just like before when I showed the 12 in the arrays broken up with the bead bars. There's more to it than just knowing 3 times 4. There's a visual spatial thing that's going to help more later on. And so as the adult, I have to require that, and I have to make it part of the class culturally. Especially when I have students who come in who don't come from Montessori or have had other types of experiences where the whole goal is to get the problems right. We have different goals in our math class. It's really about understanding more than just simply getting the answer. And if you have understanding, you should be able to get the answer. But I have to require that from the students as the adult and the setter of the environment. The last thing is that sometimes students come in, quote, knowing the rule only. And so I'll have new kids that'll come in and I'll say, oh, have you done the quadratic formula? They go, oh, I've done the quadratic formula. And I said, well, what is it? And they'll sing a song. They'll sing like negative b plus or minus the square root of b squared or whatever it is. They know this rhyme that they've memorized. And I'll say, well, that's great. What do you use it for? And they're like, I don't know. They don't understand what it is, where it came from, why you would ever use it, but they memorized it. Or I'll ask students, do you know what slope is? Oh yeah, slope. That's y equals mx plus b. Now that's a form this is called the slope-intercept form to graph a line. But what is slope? What's the concept of slope? What does slope actually mean? And they don't really know the idea. Or, I've done trigonometry, and they'll say SOHCAHTOA. SOHCAHTOA is an abbreviation for sine, cosine, tangent, and where all the parts are. But they don't know how to use it. And so, they'll say, well, I already know this already. So instead, through the materials, they get to rediscover it to understand really what it is that they're doing. And a lot of times what's funny is that students will be doing the work with the materials, not knowing. And about 3/4 of the way through, they're like, oh my gosh, this is going to get me to this rule that I already know. But they didn't even know that that's what it was going up to. And so the materials can be very powerful for students who come in already, quote, knowing the rule. But then how are they going to really gain that understanding? the materials can really help us. Okay, so time for a short quiz. Which of the following is true? Two negatives make a positive, two negatives make a negative, or two negatives can make a negative or a positive. And the answer to this question is, it depends. It depends if you're adding, then adding two negatives give you a negative. If you're multiplying two negatives, you're going to get a positive. And if you're subtracting two negatives, then you may get a negative or you may get a positive. It just depends on the context. But so often students memorize the rule, and this is the rule they memorize. Two negatives make a positive, right? Two negatives make a positive. And so, but they just use that for everything. It's not really an understanding that it's multiplication and why that happens. And then all of a sudden, then they're adding two negatives and making it positive. And so this is the danger of just memorizing rules. In the short term, it can get you solutions. But as we have more rules and as time goes by, if there's not an understanding of what's happening, then it can be very frustrating for students and those who aren't really good memorizers or students that who can't attach it to something that's real. So I was working with the student. This was a 10th grade student, so about age 16, and we were solving an equation, and she was adding 6 to both sides of the equation, and so she had to do -4 plus 6. And I said, okay, so -4 plus 6 is, and she said -2. And I said, well, are you sure? And she goes, no, it's +2. I said, are you sure? And I love saying, are you sure, for both positive and negative answers. I mean, for correct and incorrect answers. Then she goes, no, it's -10. No, it's +10. She got really frustrated. She goes, I don't know how to do it. I said, okay, stop. I said, think of the materials. And she just sat there for a second and kind of closed her eyes and said, it's +2. And I said, are you sure? She goes, yeah, it's +2. I'm like, okay, great, let's move on. So her calling back the materials gave her what she needed. And here's what she imagined. We worked these gray and green counters for positives and negatives, and she could imagine in her mind -4, and then she could imagine +6. And we know that when we have a green and a gray together, a positive and a negative, that they make 0. And so if she could see the +6 and the 4 negatives, she knows there's going to be 2 more positives than negatives, and therefore, since everything else is going to cancel out, she's going to have 2 positives left. And now she was confident of it, not because she memorized the rule, but because she could see it. She was using the materials, but not physically. She was using them in her mind. She was really working in abstraction. She pulled the essence of what these materials are out of those so that she could solve this problem, and she had confidence in it. And then if we did something like -3 plus 47, here's -3. There's like 47 there. I don't know. There's a whole bunch. Now, what's going to happen when you add these together? Not even what's the answer. What's going to happen? Well, we know that there's a lot more positives than negatives. And so 3 negatives will cancel out with 3 of the positives. So what are you going to have when you're done? Oh, I'm going to have 44 positives. So from that, can you come up with a rule? Oh, well, yeah, if the signs are different, then you're going to subtract. And why are you going to subtract? Because you're trying to find out what's left over after you cancel things out, so that you're going to figure out what's left over, what the difference is between the 2 amounts. And then whatever you have more of, that's going to tell you what the sign is. So in this case, we have more positives than negatives, so the sign's going to be positive. It's obvious why you're going to have more positives, and it's obvious to subtract if you have the materials. But if you just memorize that rule, it's just a bunch of nonsense. Like, it's something that some crazy person probably came up with 300 years ago to torture me. That's what adolescents will say. Math is here to torture me. Why should I solve any problems? Solve your own problems. I have my own problems. Leave me alone. Instead of it being a logical thing that's just very common sense. And materials can make common sense out of those rules. So when the student forgot that rule, she can recreate it as she did right there on the spot by having materials in her mind. Now, I have a clock on the side of the room, and it ran out of batteries. So I see what time it is now. I have 20 minutes. Okay, sorry. three-year journey. I was teaching my freshmen and sophomores, so those are my youngest high schoolers. So I guess ages 14 and 15-year-olds, maybe 16, about how to simplify square roots. And so I'm not gonna teach you the lesson right now, but just to give you an idea, if you have something like square root of 9, you can imagine there being like 9 little squares under the square root. But here we can rearrange those nine little squares into one big square. So we have one big square. And when we have 1, we don't have to bother writing 1. But what's the side length of that one big square now? It's no longer 1, it's 3 across. And so the square root of 9 is 3. So the side length of the square, that's the whole number. And then the number under the square root is the number of squares you had. So before we had, and if there's a 1, you just ignore the 1. So if we had 9 little separate squares, they'd be side length 1, which we can ignore, but we'd have 9 squares under the square root. We could also write that as 3. Anyway, the point is that we're doing this activity where what happens if you don't have perfect squares? Let's say we have the square root of 18. So if we had 18 little squares, could we arrange those into a big square? And the answer is no, but how close could we get? Well, we can make a square of 16, but we have 2 little ones left over. So now if I could melt, those are made of metal. If I could melt those 2 down, I could kind of pour them, along the sides, and I don't have enough to make a square of 5 by 5, but I would have 4 plus a little bit more if I could kind of, again, melt those down and put them along the side. So I know the square root of 18 somewhere between 4 and 5. I said, that's great. But let's do something different today. Instead of try to make one square, let's see if we can make same size squares that are equal to each other. So for square root of 18, instead, we could arrange them this way. So there's still 18 little squares, but now we have 2 squares of 9. So what's the side length of each of the squares? 3. So the square root's going to be 3, but how many squares do we see inside? 2. So in other words, I have the square root of 2 because I see 2 squares under my square root. That's why there's 2 under the square root. But now these squares are 3 times as big as my little square. So that's why the 3 is on the outside. So doing this activity with the materials, students can then simplify square roots. And so I gave this lesson, and there's a whole page. This is just part of it here where they have to approximate. They'd use the calculator to verify it. They then simplify it and check their work. And so some students were choosing to work on this. And I had a young lady who emailed me that night and said, I was working on this at home, and I thought I understood it, but now I don't. Can we work on it tomorrow in class? I said, absolutely, let's work on it tomorrow. So I started and I said, okay, if you have 18, can you make 1 square out of that? And she says, oh yeah, sure I can. And I said, really? We'll go ahead and try. And so she tried to take those 18 squares and she says, oh no, I can't make 1 square out of those. Well, can you make equal size squares that are smaller? And she said, so basically we're doing this right here. And she says, oh no, I can't do this. We'll go ahead and try. And then when she tried, she says, oh, I can do that. Okay, great. And then I showed her how to write it and we did that. Let's try another example. And what I found was that her issue wasn't that she didn't understand the process. She didn't really have a good idea of what her square numbers were. She didn't have an instinct about what 9 was, and that 9 was a square, and 25 was a square, that 4 was a square, and that 18 wasn't. And that can go back to what in elementary, right? When you do those materials, you know what the squares are because you're dealing with those all the time. She didn't really have that, and that was her issue. So she worked in class. I gave her a couple examples, and I said, okay, well, she said she thinks she can work on her own. So she started to work on the page, and by the end of the class, she comes up to me, and the whole thing was done. And she says, I got it. And I said, well, how did you do that? Because I was not expecting her to be able to finish it so good because how much she struggled. And she said, well, what I realized was I just made every time you make squares, they have to be perfect squares. So she made a list of her perfect squares. And she said, I just figured, well, I'm going to try to divide this number by a perfect square and I'll see how many that I have. So here's how she thought about it. She said, well, 18, I can make 2 squares of 9 because 9's a perfect square. So she divided by 18 by 9, and it was there 2 times. And then she could take the square root of 9 because the square root of 9 is 3. Now, she didn't write it out all like this, but this is the way that we would teach it in school. This is the way that I learned it. Here's the rule that you do to figure out the answer. And the reason why I don't teach it this way is several, but that middle step right there, how do you go from the square root of 9 times 2? How do you know that you can separate that to two different square roots? I was told, well, you just do it. But whenever you say just do it for a rule, then if that was 9 plus 2, you couldn't do it, or 9 minus 2, you couldn't do it. So why can you do it for multiplication? See, and there's another rule that's just going to lead to more confusion down the road. But essentially, this is what she was doing, and she was doing it mentally, and the materials got her there. Now, I said this was a 3-year journey. So the next year, we were working in an algebra class, and she was doing the distance formula, basically using the Pythagorean theorem. And I said, now, when you're done, make sure you simplify your square roots. And she said, I don't know what you mean by that. And I said, okay. So I went to the shelf, I grabbed the material, and I said, now, and I gave her an example. She's like, oh, wait a minute. I remember doing this before. She says, wait a minute, is this the thing where and she kind of explained what she's doing there, and she did an example. She's like, okay, I got it now. So just so much faster than before. The next year, she's in an Algebra 2 class, and she's using the quadratic formula. And I say, make sure to simplify your square roots. And she goes, I don't know what you mean by that. I said, okay, let me go get the material. And as soon as I said that, she's like, wait a minute, is that the thing with the squares? And you try to make the squares and you break them down and everything? I said, yep, that's it. She goes, oh, I know how to do that. And so again, by having this material, that recalled the rule for her. She could recreate it either physically by drawing it, which he would do sometimes, or by grabbing the material. But after a couple of times, she could just do it in her head. And she could do it abstractly. But it was connected to something physical. And that's what was so important about those materials. Because if it was just a rule, she's going to forget that rule all the time. And she did. She didn't even remember that we did it. But once it was recalled to her what needs to be done, she just kept getting better, and it was faster and faster every time. So that's what happens when we have that repetition. Okay, I'm going to share with you a project that a student did. We were doing factoring. And when we were doing the factoring, I would show the students how to do it with some materials, and they would go through, and when they were all done, they had to do a final project. And I always have a variety of different final projects that students can do. I try to do them from very simple to more complex. And so for the students who were working with materials a lot, their final project was going to be use materials to demonstrate these different variations, because I figured they're working with it for a long time and they could just kind of consolidate what they've done. Then I had other projects that were much more challenging, applying factoring. So doing things like calculating trajectories of projectiles, or using it to do maximization problems, and really getting in depth with the applications of factoring. So I had this one student who basically worked in abstraction the entire time. Said, I don't want to work with the materials. I'm going to figure this out all abstractly, and did that. So I thought, great, that was fine with me. Then the student was I figured they can do this really outstanding applications project. But this student, though, didn't want to do that. He was a student whose work ethic was not up to his intellect. In other words, he didn't always he wanted to put in the least amount of effort whenever possible. And so he chose for the project the one that all the slow kids are doing, using the materials, because he figured, well, that's going to be really easy to do. And what ended up happening was he already knew how to do everything abstractly, but now for the first time, he's working with the materials. So what ended up happening was that he starts doing it, and he's like, well, how do you do it with a negative number? Well, how would you do it if there was another coefficient? And all of a sudden now he knew how to do it abstractly, but he's trying to see, how do I make it physical? How do I use the materials? He came at it more like I do as an adult, where I already knew how to do this stuff because I learned it a long time ago. But to see it physically is a different type of challenge. And so for our more advanced students, we find oftentimes that if they're working it abstractly, a different challenge is, how do I make it concrete? Whereas for other students, they work with it concretely. And then the question is, how do I make it abstract? So I'm going to share this project with you that the student did. Yeah, I'm just going to share it right now. Hopefully it'll come through. I'm just pause over here. This is not factoring, but it's completing the square. And he knew how to complete the square abstractly, but now he's seeing how it actually works with the materials. Now, this is a variation on completing the square that he actually did not get to in abstraction. He didn't get that far. He did the first one in abstraction, just materialized it. But then he asked the question. He's like, well, what happens if you, now that I know how to do it physically, what would happen if you had something where you couldn't make a perfect square, like you had 2x squared? So now he's exploring how to do this because of with the materials, because the materials led him to ask the question. So now he's going to do some work with sums and difference of cubes. And I'll talk about this before we, right at the end. But with this is you're going to see the binomial cube, which is a primary and an elementary material. It's going to be the same material that we use there, but we're going to use it in a very different purpose. So those of you who have elementary training and haven't seen this lesson before, we use this with the adolescents with the same material, but we use the cube, we assign different values to it, and students can factor with that same material. So I think not so bad for a student who does not want to work with materials. And that's the thing about when, you have to find the right material for the right student at the right time. And if there's the right level of challenge there, then that's going to be right. So we saw everything from the student who was learning how to do positive and negative numbers to this student who can work fully in abstraction, but is asking questions, is trying to figure out the geometry of things, and is being really challenged by that. And those two students are in the same class. So you see all this work happening around, which is really great. So just real quick, Binomial Theorem is, this is some materials designed, this bottom one here by Camillo Grazzini. And I got a hold of this material kind of by accident. This is what it looks like. So there's the binomial cube on the left, the algebraic cube. And then, so that represents a plus b to the third power. On the right is a plus b to the fourth power. And so this is labeling that I do with my students. And I didn't get this lesson in my elementary training. I figured it out on my own. And I stumbled across this material. And when I did, I brought it into my classroom. And this is my high schoolers. And this was my, probably my 17-year-olds. And I didn't have many materials at the time in the classroom. When I brought it in, they were very anxious to see what I had. And so I couldn't stop them. They were just like, well, can we at least see what's in the boxes? And so here are two, this is my most advanced class at the time of 17-year-olds doing a sensorial exploration of the materials, trying to figure out what these things do. and they kind of begged me. They wouldn't let it go, so I ended up having to give them a lesson. So I got one student to get a picture of of me giving them the lesson. And they were just like, okay, just figuring out what this does and what it means was just awesome for them. This is another class of students that I gave the lesson to, and I said, well, I only had time to give the fourth power material. This is the fifth power material. I said, if you want, you can go ahead and explore it on your own. And you can see in the background, everybody wasn't interested in it, but these two young ladies were. And what's very interesting, I love this photo for a couple reasons. The girl on the left, she's long graduated from high school. She went to university, went to Carnegie Mellon, which is a very prestigious university here in the United States. And I think she ended up majoring in like biomedical engineering, something like, she's probably making cyborgs or something like, or curing the coronavirus. She's doing something like that now. The young lady on the right, after high school, she left, did not go to university, at least right away. She instead went around the country doing political protests and activism, and eventually opened her own art studio. What's interesting is that as far as their mathematical interest and abilities, total opposite ends of the spectrum, but both are extremely engaged in this material. It appeals to students all throughout. And what I love about the photo, the second thing, is the girl on the right always had headphones on. She said, I can only concentrate with headphones on. That's how I focus. But here she's doing this work, and look at the headphones in the picture. They're off her ears. It's kind of like when you see the young child who kind of sticks their tongue out to really concentrate, where they're really focused. She's like, I got to be here. I got to be present to do this work. And so they did this labeling. In fact, they were so excited to do this. The papers, they didn't even cut the papers. They just kind of tore them up to label. And then they said, well, are there sixth powers material? I said, well, no, there's not. And they said, well, for a project, instead of doing whatever else I was asking them to do, they said, can we build them for our final geometry project? I said, yeah, go ahead. That would be great. And so this is their work on paper about how they were figuring out what would go to a plus b to the sixth power. And what's funny is that the girl on the left, she could multiply it out. Like, she could just do the algebra to figure out what it was. But she wanted to figure out where the pieces came from. And so she has these diagonal lines going from a plus b to the fifth to a plus b to the sixth. And she's basically doing the counting to figure out how many pieces of each type there would be. And so what I said to her is, I said, oh, well, I see that you used Pascal's triangle to figure this out, which is the way that I would teach how to use the binomial theorem. We would use Pascal's triangle. So I said to her, oh, you used Pascal's triangle. And she said, what's Pascal's triangle? And I was like, well, first of all, I felt silly, because I'm like, how are you a high school sophomore or junior, and I didn't teach you the Pascal's triangle yet? But also, like, she discovered that on her own. Like, that she discovered that through the material work, which is awesome. And then underneath there, I said, well, what would a to the seventh look like? And she was able to just write it out without doing any calculations, because she understood where that came from. They didn't finish by the end of the year, but she wanted to continue it. And so this is her the following year. I couldn't find her, and outside during class, and outside she was sitting in the hallway. And on the right in the cardboard, that's her trying to build the sixth powers of a binomial. A couple years later, this is another student who was a Montessori lifer. She had to do a final senior project in math. And she said, I want to do something with the cube. I remember the cube when I was a little kid, and it was a trinomial cube. And she remembered using it, but wasn't quite sure what it was for. And so there's my elementary album, and she's reading my album and trying to understand what the trinomial cube does. Now, with the trinomial cube, she knows how to do it algebraically. She wanted to expand it. So to do, like, instead of a plus b plus c cubed, she said, well, what would happen if you had a plus b plus c plus d cubed? And that's something that kids in elementary school do as well. But she's like, well, she said, I know how to do it algebraically, but I want to understand how the cube works. In other words, she was interested in how many different pieces would I have, and what would the different shapes of the pieces be, and why. So she's doing this analysis of materials to understand the abstraction, which was very cool. I think I have to end here, but I'm just going to say the last thing is that we generally have three types of materials that we use for the adolescent. One of them is Montessori materials that we've adapted. So you've already seen that today. You've seen the binomial cube, but we do it in a different way. I use the powers of 2 and powers of 3 material, but we'll use those for negative exponents and fractional exponents. We'll use materials that are new to Montessori. So the Algebra Tiles, those are something that have been around for a very long time. They actually had their origins in Al-Khwarizmi, who was an Arab mathematician known as the father of algebra. He saw things geometrically, which also was inspired by Euclid, seeing things geometrically. But we've adapted those and then make them fit in with what we're doing in the Montessori. What the kids have done in elementary, we do the Algebra Tiles in a way that makes sense in a Montessori environment. Plus, we invent new materials to so students can work with that, like the coordinate grid, and that's physical that we can work with. And the third type is historical materials, kind of like a museum of machines. So these are some that I had in my classroom. We have slide rules. And it's not so much just it's not so much how do you use the slide rule, that's part of it, but why does the slide rule work? What's the mathematics behind that? And it's based on logarithms. And so when we do exponents and logarithms, we study the slide rule as a tool. We have Napier's bones there. On the left is called the planimeter. That's a device which can actually calculate the area of shapes. If you trace the shape with that little sight there, the gears turn around, then it gives you the area. So how do these things work and what's the mathematics behind them is a great way to bring in materials as well for our students. Yeah, so I guess my main point is that there's something there for everyone. If the materials are appropriate, if you allow students to use them in their own time, if you question them about the materials, if you make it part of your environment, it's going to bring wonderful things out from your students. And again, sometimes students are resistant at first, but again, I've had so much success with materials because we've created that environment. And I don't force the materials on students, but I force the environment on students. And it's through that environment that they end up loving materials because they come to it in their own way at their own time, what's appropriate for them. So I see that's my time already, so I'm going to have to stop there. Erin, any closing words or anything?
No, if you have any questions for Mike, you can reach out to us at themathinstitute.org and send us a question. And if there's anything that's a question that comes up about something from this session and you send it to us, we can address it. Mike can address it at the next session. So since we're out of time, we won't be able to take any questions, but you can always write to us. So
yeah, and it's my fault because again, my clock I think is running low on batteries. I thought I had 10 extra minutes when I looked up, so I got behind. But Erin, if you don't mind, I'm happy to stay an extra 5 minutes if people do have questions. I would love to answer a couple because I mean, I should do a couple questions. You can go if you want, but I'll answer questions for five minutes or so if people have them. Can I do that?
all righty, all righty, folks. Yeah. You heard him. What happens when they cannot visit the materials to recall the concepts? For example, if they're at college? Yeah, that's a good question. That's good.
Yeah. So, I think what happens then is, if they've internalized them, like, okay, so for completing the square, for example, they're not always going to have those algebra tiles with them. But I had a lot of students though, that when they would do the drawing instead of actually doing the numerical thing. They just saw it quicker if they drew it. So it's like they have the materials with them because they can draw them, because they can recall them. And I think the other thing that happens then is if they're in college and they can't, go back to the materials physically, if they've had a strong enough connection with what they've done, then like that young lady who was doing the simplification of the square roots, just seeing it is like, oh, wait a minute, I know how to visualize that. I know how to make that real. And I think the biggest gift we can give them is to know that everything can be seen. Everything has a reason. Like that's the hardest thing to learn about in math. And for me anyway, once I convince myself that nothing is magical, there's a purpose behind everything. And I am smart enough to understand it if I just want to take the time. So if a teacher gives you a rule and you don't understand it, you can figure out a way to make that real. You can see what's really happening there. You might have to go do that discovery on your own, but it exists. And so at least having that knowledge with them, they can go figure that on their own. And they know at least to go look for resources or to ask the questions or to connect it to something that they've already done. And again, hopefully the goal is that students are an abstraction. And so they can do a lot of the stuff later on, but they know that rules have reasons. And I think that's the biggest thing that we can give them. And so they can figure out the reasons for themselves.
All right. Nice job, Mike. The hour
Sure.
always goes by too quick.
I know it does. But it's great to see everyone. I saw Francoise on the call. I hope you recognized a couple of those students. I think they were yours as well. I saw her on the call. Yeah. And a couple people asked, I got a couple direct messages about teaching multiplying negatives, making positives using Montessori materials. Keep an eye out for some of the workshops that we do. I know I'm doing a couple workshops in the summer and the fall. I do some workshops on integers and kind of the very basic algebra stuff. So if you join that workshop, I definitely cover those topics there. So I'd love to do that. So yeah, so go ahead and join the workshops if there's something that really appeals to you. For those workshops, I do a lot of work with the materials. I just finished one on factoring, and it was like 6 hours of just working with the algebra tiles, showing how things fit together and so on. So if you're interested in getting more specifics of materials, then we have the workshops for those. So that'd be great.
All right. And we'll tally up whether geometry or seminar one for next week. It looks pretty close. Seminar might have the edge, but we will let you know in some communications this week. Thank you, everybody. Thanks for all that you do. Thanks for all you do for your students. We appreciate you. Have a good night. Take care.